know that Alibre cannot do this particular operation, but there you go. We did it with math. Hello guys and welcome to today's video. Now today we will be making the flat pattern for an Auger flight, which the sheet metal environment in Alibre cannot do. But I'll show you how to do it. Let's get to it. So the sheet metal environment in Alibre cannot handle this particular job. So I will be using the part environment, and I will call my part the Auger flight. Okay, now the first thing I will do is I will go into my equation editor and start making some equations. So first one, flight OD. Let's go with a flight that has a 300 millimeter outside or outer diameter. Then we'll make the internal diameter and we'll make that 88.9. So 88.9 millimeters is the outer diameter of a DN80 pipe, which corresponds precisely to the 3-inch NPS pipe, outer diameter that is. So let's do that. What else do we need? Well, we need the pitch. I'm going to call this flight pitch. I'll give that a value of 100. And I also need the flight thickness, flight thick. And I'll go for a 1.2 millimeter thick sheet. So that's all we need for now. And we'll go now and design the 3D shape of the Auger flight, right? So the flights of an Auger, not an ogre. I guess Auger and Auger are different. So the flights of Auger are all cut individually, and then they're stretched, and then they're welded onto the Auger shaft, and that's how you create your Auger. To my knowledge, there's not a way to manufacture a continuous helix that then you fit over the shaft and you weld it. At least not a economically viable one. The way Auger flights are designed in 3D is pretty simple. We will design in the in the XZ plane because I want my flight to go up along the Z axis. So I will be designing here. I've got my trine here telling me, look, the Z axis points downwards. I will reset my view. Now it points upwards and I'll start a rectangle. So this distance is going to be the flight ID divided by 2. Don't make that mistake. I've done that mistake many times. And this, not a line, but this horizontal dimension is going to be flight OD divided by 2. This is probably, yes. So I've made a spelling error here, which when I correct it, this red equation is going to not be red anymore. There you go. I'll click OK, and I'll click OK here. Okay, now this then, which is a driven value, is a parameter now. That's the width of our flight. So I'll go into my equation editor again, and I will rename this into flight width. I'm using very long names. That's not going to be practical in a little while when we'll be writing some large equations, but I think it's easier to follow for now, and you can use shortened names when you do this. So I'll just hit OK. And of course, this is the flight thickness. Okay. And finally, I just need to make this bottom point horizontal to here. So now I've got this section of my flight that is sitting on the XY plane, and it's going to helix upwards along the Z axis. Okay. So first of all, this is my axis, okay? And I want number of revolutions and pitch. So this is going to be 1 revolution, and this is going to be flight pitch, okay? And that's it. That's what I need to make. And I make lots of these, and I weld them together and to the shaft, and I make an auger. So if we look at this from the top, right, clicking on the outer edge, Alibre, measure this. Alibre gives me a length of 947.75, and the inner length is 296.64. Notice that it's not giving me diameters. Maybe if I click this face, then it's giving me radius, which is correct. It's 150. But when I click on the edge, I'm getting lengths because these are no longer arcs, guys. Okay. But what are they? Well, so let me look at it from this angle, right? So you see this shape, right? This is the projection of how the edges move along the pitch. So now let's look at this picture. So what we have here is the equations on how to create a auger flat pattern geometrically, right, with equations. Okay, so you see that we're projecting a circle along here, and we're getting this shape. So 1 through 7 is, well, half this projection, and A, B, C, D, etc. is the inner one. Now, looking at it from this angle, it sort of becomes clear that the outer edge has a length that is a lot longer than the inner one, right? It covers a lot more distance, and you can see it here as well. It covers a lot more distance than the inner one. However, if you click on both of these, right, and measure, what Alibre is going to give you is going to give you a delta x. So that's the distance between them, and that needs to be constant along the entire flight. So when we cut the shape of the flat pattern, we need to cut a circular shape that has this radius, a radius that would create this arc length, right? We need to cut an outer radius that would create this arc length, and then we need to have a constant width of what we just measured, which was 105.55. And with these three parameters and constraints is how we get this C shape, which is the flat pattern of the auger flight. And that's why you get this little opening here. Now, about these equations, how do we get these equations? So this equation is easy enough to understand how we get to it. If you take the outer cylinder along which this helix is climbing, right? If you take this outer cylinder here, the 300 millimeter OD cylinder, and you unroll it, right? Imagine that this is inside a cylinder which you unroll. Then the shape would be a rectangle. If you unroll that cylinder, the shape would be a rectangle, and the bottom line of it, right? So the horizontal sides of that rectangle would be equal to the perimeter of that cylinder. Now the perimeter of that cylinder is 2 times pi times the radius, or the diameter times pi. The vertical sides of that rectangle would be the pitch, because that's how high up you're climbing along that cylinder. And this edge would then trace a straight line from the bottom left to the top right, would trace a straight line along this unrolled cylinder. And that straight line would create a right angled triangle. Now, we can easily calculate the length of the trace of that flight because it's the hypotenuse to that right angled triangle, and that is the square of the perimeter plus the square of the pitch gives us the square of the length of the hypotenuse. And that's how you get this first equation. D times pi, that's the perimeter, plus h, that's the pitch, if you look at this, this chart here. Okay? Now, in the interest of visualizing this, let's make a sheet metal part. And I will actually show you this, this happening. So I need to make a pipe, a sheet metal pipe. And how do I do that? I make it as a sheet metal cone with the sheet metal cone tool. I have found this to be a lot easier, right? And this will be, well, let's make it 120. You will see why. Okay. So now, right, I will come in here in the model environment. I need to save my Auger flight first. Save it here. And I want to go and do a Boolean subtract with that Auger flight. Yes, okay. Let me show my reference geometry for this. So basically what I want to do is I want to have this coaxial to this, okay? And I want to have this at a distance of 10 millimeters to this. I don't want to cut, oh, wait. Okay, so I see what happened here. So if I click OK, nothing will happen because when I made this lofted flange, I made the thickness towards the outside. I need to make the thickness inward and then, okay. So this is the trace of my Auger flight. So when I give it, when I make the flat pattern, okay, well, let's fix it. We can fix this. We can fix this. What we need to do is we need to spin this around so the start of the Auger meets the start. There you go. Let's get our reference plane going again and make these two. And now, when I get my flat pattern, there you go. So this is the visualization of what we just did. And that's why you can get the length of the trace of that Auger flight from this. So coming back to our flight pattern here, we have discussed how we get this value here, which is for the outer edge of our flight. The exact same procedure is followed to get the arc length for the inner side, for the inner edge of the flight. The width is always the same, as we said, we know that. So let's go ahead and open our equation editor here and start putting these dimensions in. Okay, let's have this showing just as a reference. Okay, so my U arc large is going to be the square root, well, yes, the square root of the perimeter, which is flight OD squared times pi squared plus the flight pitch squared as well. So that is going to be wrong. Okay, so this is wrong because I put in an asterisk there instead of raising it to the power of 2. Now, if we fix that, okay, so then we get 947.76. So guys, when we get there, well, it's not exactly the same. I'm not sure why, but it's pretty damn close, right? It's pretty close. It's probably a rounding error because we get to a huge number, which is like 880,000 or something, and then we square back down. That's probably a rounding error, but still, we're getting a very, very, very decent number here, very close to what Alibre itself is measuring for the arc length. So we must be doing something right. Let's go make the small one, and that's why I mentioned that the parameter names are not case sensitive. I will put in a small u there because it helps me visually when I'm looking at the equation editor. But I cannot say capital U lower dash arc and then lowercase u lower dash arc because that's the same parameter name if we account for the fact that they're not case sensitive. So let's go here, right? So this is the flight ID squared. Oh, well, it's the square root of all of this, right? So it's the flight ID times pi squared. Let's get this correct this time. Plus the flight pitch squared. So this is going to be a significantly smaller number. Why is that? Because if you unroll the inner cylinder, the perimeter, which is the length of the horizontal sides of that rectangle, they're going to be a lot smaller, right? So we hit apply. 296.65. Let's click on. Let's hit OK. 296.65. Close enough for us to work with. Okay. So now we have these values. What do we do with them? Well, we need to get that inner arm. So we found the arc lengths, right? But how do we design this flat pattern? Actually, how do we get the small radius and the larger radius of this flat pattern? And how do we get the angle here? Well, the small radius is beta b, which is the width, times the arc length of the inner edge. And you divide all of that by the difference between the arc length of the larger edge minus the arc length of the lower edge. So the way to get to this pretty quickly is you define the small radius and the large radius to be the arc length, we just calculated, times this times the angle theta that it goes around for in radians. You do that for the small inner radius and you do that for the larger outer radius. And then you take these two equations, you divide the two equations, and that's what you get. I've prepared a Word file that you will find a link to down in the description, and you will also find a link to that Word file in the Alibre forum, which goes through this entire process in a bit more detail, right? But basically, you get to the smaller radius like this, and then you add the width, and you get to the larger radius. So let's do that. So flat r is the width, right? So we're starting a parenthesis here. The width. The width is that driven dimension we have, right? Which is here, flight width. Okay, let's get that. Flight width. Okay. Minus the small arc length. Okay, now we divide all of this by the difference in the arc lengths. All right, arc large minus u arc small. So it's probably another spelling error here. No, it's not. I'll tell you what this is. So if I click apply and I hover over it, I'm getting, oh, it's syntax not valid. It's not a dimensionality error then. I thought that maybe if I do this, that fix it. But it doesn't because it's not a dimensionality error, it's a syntax error. Ah, okay. So I've named this arc mall. My keyboard is not having the best time of its life. Now this is arc, and now the dimensionality is not valid. So now if I do this, and it works. Okay, so the reason this didn't work Okay, I'm getting a negative number here, and I think I know why. It's because I subtracted here and I should have multiplied. And now that I've multiplied, I no longer need this for dimensionality. Okay. So the way this works is you see in the pop-up the equation here, you multiply two distances on the top of that fraction and you get a distance squared, which is area. And then you subtract two distances. The subtraction of two distances is still a distance. So on the top you have distance squared, on the bottom you have distance. So the result comes as distance to the power of 1. That's why it accepts it. Now the way I had defined this equation earlier, it was distance divided by distance, came out with no units, and that's why adding the times 1 millimeter helped. But now this is the correct equation, right? Flight width times the small arc length divided by the difference of the two arc lengths. Okay, so that's the small r. And how do we get to the angle? Well, the angle is 360 degrees times the small arc length, because that's the r that we just calculated. So times the small arc length divided by the perimeter, right? Which is 2 times pi times the small radius, which we just calculated. Now, in this equation, 360 and the 2 from the denominator I've cancelled out, and you get the equation 180 times u divided by r times pi. That's just, saying that on the bottom you have the entire perimeter of the inner cylinder, and on the top you get the arc length, right, which is the portion of the perimeter you're actually using, and then you're multiplying by 180 just to make that degrees, because the CAD system understands degrees, right? So let's go plug that in as well. So we have the flat angle being 180 times the small arc length. Okay, I actually need to put this into parentheses, divided by this radius we just calculated times pi. This is an angle. Yeah, wouldn't work as a distance, but it does work as an angle. Hit apply, and we get. So this seems to be a bit weird, right? This seems to be a bit weird. First of all, when I get it, small differences here create huge differences up there. That's not how this is supposed to work. What's that telling me is that we have another problem with dimensionality. So to solve more difficult problems with dimensionality, you make unit parameters, right? So u arc small is a distance, right? 180 in this context is nothing. Well, maybe if I actually write degrees there, will this work? Hey, that worked. Okay, so I didn't even need this. U arc small is a distance, flat r is a distance, and pi is a unitless number. So it was dividing and it was getting a unitless number, and it didn't know what to do with it in the angle type. So as soon as I said 180 deg, which is the definition for degrees, it worked. And now we don't get these wow shifts anymore. Yeah, there you go. That is the correct angle, 353 degrees, and so on and so forth. So now I hit OK. I don't need this anymore. And what I'm going to do is I'm going to go here and first of all edit this configuration, make only feature suppression available in the configurations, and call this 3D shape. Then I'm going to make a new configuration based on that and call it flat pattern. Active, and I will suppress this. Now I will go into the XY plane, start, whoop, sorry, wrong command, start a center arc, make these 2 points vertical so that, you know, they are symmetric. And now this is going to be flat R, okay, and I'm making 2 auxiliary lines here, and this is going to be 360 degrees minus the flat angle, which will give me 6.55 degrees. Yep, that's correct. Okay, that's good enough. Now another center radius, and we'll say that these points are vertical with each other, and we'll say that this one falls onto this line, and I'll connect it with a couple of lines, and I can say that the length, the aligned dimension of this line is our driven dimension flight width. Now I will extrude for flight thickness, and that is our flat pattern. Okay, so 3D shape, flat pattern. It almost works like the sheet metal environment. Isn't that cool, guys? This is such a difficult thing to do. I don't know that a lot of CAD systems can do it. I know that Alibre cannot do this particular operation, but there you go. We did it with math. Okay, so let's recap. This is the geometric flat pattern. It doesn't take into account stretching, deformations, thinning of the material, all that. If you get this angle to be more than 30 to 40 degrees, this inner angle to be more than 30, 40, 50 degrees, you're pretty close to what the geometric approach can give you, for example. And this happens for large pitch values. So if I make this like 400, right? I hit OK. So this is, I'm not sure this will work. If you stretch this, I'm not sure it will have a 400 millimeter pitch, right? You see this is definitely not. But for pitch values that are, reasonable, and you can input what's reasonable for you there, this will work. This will give you a flight that will work within a few millimeters, if not with accuracy less than 1 millimeter. So there you go, guys. I hope you liked it. If you did, hit the like button, hit subscribe, and I hope I will. Hey, what are you looking at? Stop looking at my EasyCam. My eyes are down here. I see you, and I'll see you in the next one.